You have heard the old saying, "A watched pot never boils." A proverb about impatience, but in quantum physics, this is not a metaphor. It is a literal, experimentally verified fact. If you watch a quantum system closely and frequently enough, you can actually stop it from changing. Decay stops, movement stops, evolution freezes. This is the Quantum Zeno Effect, named after the ancient Greek philosopher Zeno, who argued that a flying arrow never moves because at every instant it is stationary. Welcome to Großdenken, everyone. Today, we are going to explain exactly what this effect is, the experiment that proved it, and why it matters for quantum computers. Please support this channel grow by just subscribing. That would mean a great help. In 1977, physicists Baidyanath Misra and E.C. George Sudarshan at the University of Texas made a shocking theoretical prediction. They considered an unstable quantum system, like an atom in an excited state that is about to decay. Normally, if you leave it alone, it decays after some average lifetime. Standard quantum mechanics, but they asked, what if you repeatedly check whether the particle has decayed or not? What if you measure it over and over again, very rapidly? Their mathematics produced a stunning result. If you measure the system frequently enough, the decay slows down. As the measurement frequency increases, the decay stops completely. The system freezes. This was named the Quantum Zeno Effect, because constant watching prevents change. Why does this happen? It comes down to one weird feature of quantum mechanics. Measurement collapses the wave function. Here is the crucial detail. For extremely short time intervals, the probability that a system changes from its initial state is not proportional to time. It is proportional to time squared. That means near time zero, the graph is almost perfectly flat. The system barely has any chance to change in an extremely short instant. When you perform a measurement, you collapse the wave function back into the initial state. Then the evolution starts over from zero. If you measure rapidly enough, the system never gets past that flat, low probability region. It never has time to decay. You freeze it. Each measurement resets the clock. Measure fast enough and the clock never ticks. For decades, this was just theory. Could it be observed? The challenge is that you need to measure extremely quickly. In 2015, physicists at Cornell University provided clear experimental verification. They worked with about 1 billion rubidium atoms cooled to near absolute zero. The atoms were suspended in a lattice created by laser beams. At these ultra-cold temperatures, the atoms could tunnel between positions, a purely quantum behavior. The researchers then used an imaging laser to observe the atoms. When the imaging laser was off, the atoms tunneled freely. When they turned it on and made measurements more frequently, the tunneling dramatically reduced. The atoms stopped moving. As lead author Yogesh Patil said, "This gives us an unprecedented tool to control a quantum system." The watched quantum pot literally refused to boil. But here is where it gets stranger. Under different conditions, the opposite can happen. This is called the Anti-Zeno Effect, where frequent measurements actually accelerate decay. Whether you get the Zeno or Anti-Zeno effect depends on the details. The measurement frequency, the system's environment, and how the measurements interact with the system. Both have been observed experimentally in trapped ions, ultra-cold atoms, and superconducting circuits. The Quantum Zeno Effect is not just a curiosity, it is becoming a practical tool. Application 1. In quantum computing, qubits are extremely sensitive to environmental noise, which causes them to lose their quantum state. By applying frequent measurements in the form of control pulses, engineers can use the Zeno effect to freeze qubits in their desired state, protecting them from errors. Application 2. Scientists at Fermilab are now exploring using the Quantum Zeno Effect to suppress background noise in superconducting qubits used to detect dark matter. By freezing unwanted defects in place, they can dramatically improve the sensitivity of their detectors. A crucial clarification. The Quantum Zeno Effect is not caused by human consciousness or a mystical power of observation. If that were true, particles in a cloud chamber where every decay is continuously tracked would never decay at all. But they do decay, exactly as predicted. The effect only occurs when measurements are so fast that they outpace the system's natural evolution time. For typical radioactive decay, that natural timescale is about 10-21 seconds, far faster than any measurement device can achieve. The effect is real, but it requires specific conditions. So Zeno was both wrong and right. His arrow clearly moves through the air. But 2,400 years later, his paradox found an unexpected home in the quantum realm. The Quantum Zeno Effect proves that in quantum mechanics, looking is not passive. To measure is to interact, to observe is to influence. A watched quantum system does not boil, it freezes. If you want more experimentally verified weirdness from the quantum world, hit subscribe.